Video 6. Multiplication and its relation to products. Introduction. This episode deals with the concept of multiplication considered in the context of cognitive products outlined in the previous video. One could legitimately wonder whether we really need this new interpretation of products, which only seems to complicate further an already difficult subject. To answer this, consider the conflict existing between the common sense idea that multiplication makes things bigger and division makes things smaller, and the mathematical assertion that such an idea is an obvious misconception. To support this claim, teachers of mathematics tend to bring up the case of multiplication involving fractions. The next slide shows an example in which a pie pastry is multiplied a quarter of times. The process below is typically interpreted as cutting a pie into 4 equal parts, one of which is then selected as a result of the multiplication. This procedure is not problematic because pies, areas, lengths, volumes, and other uniform objects are infinitely divisible into equal parts. However, not all entities can be divided into equal parts, as many of them are non-uniform and often irregular. Other objects or systems cannot be divided at all without losing their own integrity and functionality. In such situations, the act of multiplying them by a fraction becomes problematic. As an example, consider multiplying a functioning bicycle 1.5 times. Whichever way the bicycle is cut in half, its functioning is lost. Only when replicated as a whole will the bicycle be able to meet human expectations. For this reason, all acts of repeating, replicating and multiplying can only involve natural numbers. We can overcome this cognitive restriction only through better understanding of the human experiences. When we look, recall or imagine an object, we experience it with respect to its properties. Consider a bicycle. We know it in terms of its size, color, comfort, weight, expense, usefulness, and other such experiences. When a bicycle is cut into parts, most of those properties become irrelevant. However, when the bicycle is functional, each of those properties can be experienced separately as a product of the intensity of the property under consideration and its extent. The price of one bicycle is then a product of value of 1 unit times the number of units. If 1 unit costs $100, then 5 bicycles would cost $500. A half of a bicycle, however, is worth nothing unless it is sold for parts. To avoid cutting one of 2 bikes in half, we have to turn the 1.5 repetition into a natural number by decreasing the value of the unit. The bicycle of $100 value times 1.5 equals $100 divided by 10 times 1.5 times 10 equals 10 times 15 equals $150. The smallest repetition in this case is 15, but any larger number derived in the above way will produce the same result. Similar thought process takes place when multiplying numbers rather than objects. In the example below, the first factor represents a value of a number and the second one the extent of repeating this value. 1 times 0.5 equals 1 divided by 10 times 5 times 10 equals 0.1 times 5 equals 0.5. Common sense suggests that repeating only a half of a unit is not logical because repeating means duplicating the unit in its entirety. The extent of repetition has to be a whole number, for example 5 instead of 0.5. When 0.5 is multiplied by 10, 10 new levels of 1/10 values have to be evoked within the unit to ensure that we are dealing with the same product. This is illustrated in the next slide, which uses water in a container to demonstrate the change of value. To compensate for the tenfold increase of repetition from 0.5 to 5, the unit's value has to be scaled down to 1/10. But first, 10 new scales have to be invoked within the unit. Then a unit with 1/10 of the value can be repeated 5 times. The process of creating new levels of water within the container is referred to as differentiation, which is discussed in video 7. Such procedures can be easily turned into a familiar algorithm of decimal multiplication as displayed below. Please notice that we always multiply whole numbers and only then take care of the decimal point. This and many other rules and procedures, which most of us learned at school, have replaced the intuitive reasoning we use every moment of our lives. Constant product. The procedures in the previous slides are possible because all products are defined as totalities of unique associations between intensive factors and their extensive repetitions, which means that the association 24 times 1, 12 times 2, 8 times 3, 6 times 4, 4 times 6, 3 times 8, 2 times 12 and 1 times 24 all stand for the same product of 24. This is represented graphically in the next slide. This property of products is represented in the figure on the left, which shows all unique associations of the product 24. If unfamiliar with the cognitive product idea, please check video 5. Despite of their differences, all forms of 24 represent the same product. To appreciate this, one has to consider what it means for the product to be identical. Identical products. Two products are identical only if they share the same unit repeated the same number of times. To be made from the same unit, the products have to share the intensity or value of their common properties. In the examples below, this means that the two product representations, two groups of 6 squares, have the same number of levels and columns, 3 and 2 respectively in this case. Equal products. This is not the case when one of the products changes its shape. For example, it is rotated by 90 degrees as shown below. The two products are equal, but no longer identical in the sense above. The number of scales in the second product decreased to 2, but repetition increased to 3. So the two products, described in video 5 as the totality of unique associations between scales in the unit and the unit's repetition, remain equal. On this view, the products in the previous slide are not only identical but also equal. On the same basis, such products as 6 times 1, 1 times 6, 3 times 2, 2 times 3 are all equal. There are infinitely many forms of such products. For example, 6 can also be the product of 0.1 times 60, or 0.4 times 150, or 1/3 times 18, or 1/27 times 162, etc. See the animated example of 1 times 6 equals 0.5 times 12, which is displayed below. Please note that the repetition of each unit is always a natural number, which reflects the idea that the unit can only be repeated as an intact whole. It is this property of constant product which is used in various algorithms of multiplication we all learned, automated and entrenched while at school. Conclusion. The issue whether multiplication makes things bigger and division makes things smaller is of little consequence to professional mathematicians. It is a purely educational problem of great interest to teachers who, in their daily dealings with students, face the unnecessary conflict between human intuition and mathematical practices. The apparent conflict vanishes as soon as we realize that mathematical concepts are complex ideas based on simple intuitive notions. This means that neither intuition nor mathematics are wrong in their claims. They are both true and correct within their respective contexts. They both have specific role to fulfill, and this is why it is important to relate them together correctly. The cognitive interpretation of products provides such an opportunity. It connects students' private intuition with the public world of mathematics and eliminates any tension existing between them. The issue of multiplication and division is only one of many apparent conflicts between our common sense and mathematics. I hope that the video helps to clarify these issues. It is intended to encourage teaching mathematics in well-established and proven ways, as long as the connection between mathematics and intuitive thinking is provided. The students need to know not only how to do math correctly, but also where the procedures they have to master came from. I am looking forward to your comments and questions. Thank you. All ideas in this video come from a book published in 2014 under the title Conceptual and the Structure of Human Experience. The book can be purchased from Amazon.